to this video lecture. Let us take a look at this example. So we want to determine if this integral is divergent or convergent. Okay, and of course we will use the comparison test. So before we do anything, let us make a guess as to whether this integral will be convergent or divergent. So if we, so this is not mathematically rigorous, but it will help us to understand our reasoning. So you can think of this as just making a guess as to which way we will go. Are we going to try to prove that this integral is convergent, or are we going to try to prove that it is divergent? So if we think about this expression, x squared plus 1 over x cubed plus 1, if x is very, 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 very large, let's say like 10 to the 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 10, then this plus 1 hardly has any effect on the size of the numerator. So let us ignore that. And similarly, this plus 1 as well. And then we see that this expression is equal to 1 over x, which is, if we think about the integral from 1 to infinity of 1 over x, this diverges by the p-test. So we are going to try to prove that this integral is divergent. And why do we do that? That is because we kind of guess that this expression, x squared plus 1 over x cubed plus 1, kind of behaves like 1 over x. So that is our guess. So let us be very clear here. We are guessing. We have not proven anything yet. Okay. So what will we do? So let x be greater or equal to 1. Then what can we see? Then x cubed plus 1. So if x is bigger than 1, then this 1 is smaller than x. X cubed. So I'm going to write it this way. If x is bigger than 1, then of course 1 is less than x cubed. So you can let's write here, this is because the function that sends x to x cubed is monotone. And 1 cubed is of course 1. So this 1 is less than x cubed as well. So we get that x cubed plus 1 less than or equal to x cubed plus x cubed, but that is just 2x cubed. Okay, so that is our that is this expression. And now since x is greater than 1, everything is positive, so therefore we can see that 1 over 2x cubed is less than or equal to x cubed plus 1. So all we did was we took this inequality, took the left and the right, and we cross multiplied. Everything is positive, so the direction of the inequality does not change. Okay, and also if x is bigger or equal to 1, actually let me write it this way around. If x is if 1 is less than or equal to x, what do we have? we've got x squared plus 1, and x squared is non-negative, and if we just forget about this 1, so or in other words, keep in mind that 1 is greater or equal to 0, then x squared plus 1 is bigger than x squared. And now let's see what happens. So let us reiterate here, under the condition that x is bigger than 1, we've got, let's take a look at our expression that we are interested in, x squared plus 1, that is bigger than x squared, over x cubed plus 1. But x cubed plus 1, here we have seen that that is x cubed plus 1 is bigger than 2x cubed. So this is bigger than x over 2x cubed. Whoops, I missed a square there. And there as well. 2x cubed. And this is 1 over 2, 1 over x. So now we see this expression is bigger than that expression. Okay, and now we see here what happens. Here we've got the function that sends x to half 1 over x squared, and the integral, or the improper integral, of this function diverges, and the improper integral that we're actually interested in is bigger than this integral that actually diverges. So our conclusion will be that our integral diverges. So since the integral from 1 to infinity of a half 1 over x dx diverges, why does it diverge? That diverges because of the p-test. Our exponent here is 1, so that is one of the cases that diverges. And since x cubed plus 1 over x squared plus 1 is bigger or equal to 1 over 2x when x is bigger or equal to 1. We have that the integral from 1 to infinity of x cubed plus 1 over x squared plus 1 dx diverges by the comparison test. Okay, and that is it for this example. And notice here we did not explicitly compute this integral. However, we do not need to. We can use a simpler integral to show that this integral actually diverges. Okay, and that is it for this example. I will see you in the next one.